Hello everybody. In this video we're going to be covering section 14.3, relative strengths of acids and bases. We're going to learn how to assess the relative strength of acids and bases according to their ionization constant. We're going to rationalize trends in acid-base strength in relation to molecular structure. And we're going to carry out some equilibrium calculations for weak acid-base systems. So first thing we need to do is make a clear distinction about what is acid-base strength. Okay, people have kind of a confused idea sometimes about this. The strength is merely the amount by which it ionizes in water. Okay, how much of it is going to ionize in water and produce those hydronium ions or hydroxide ions. All right, a strong acid or base ionizes nearly completely. There's not that many of them, and here's a little table of some common ones that you may see. Okay, if little of the acid or base ionizes, it's considered a weak acid, and the majority of acids and bases are weak. There, as we've done with Kw and many other things, there's an equilibrium constant for acid reactions. And this equilibrium constant is going to quantify the relative strength of the acid. So if we had a model reaction like this with this generic acid, this would be its equilibrium constant. And again, we're not going to include the liquid water in it. And you can see that as the ionization happens, so as these concentrations here go up, this one's going to go down and Ka is going to become large, whereas if these were small, there would still be a significant amount of unionized acid. Ka would be small. So the larger the Ka of an acid, the larger the concentration of hydronium and its conjugate base. Ka approaches infinity for strong acids, and we're going to see that that actually can pose a bit of a problem for us. The Ka of weak acid is determined experimentally and tabulated. So we know the Kas for most weak acids. There is a abbreviated table in Appendix H that we're going to be using for our problem. So if you need to know the Ka for a specific problem, chances are you're going to go find that in Appendix H of our textbook. We can relate acids in their strength. Okay, for instance, I could make this relation where I have acetic acid is less strong than nitrous acid, which is less strong than hydrogen sulfate here. And I would know that because I would go to the table in Appendix H. Okay, I could write out their ionization equations and then look up their Kas. As the Kas go up, the strength of that acid increases. Just like we had Ka for acids, there is a similar base ionization constant, and it follows the exact same rules. The stronger the base, the larger the ionization constant. If we had a model reaction like this, where we're accepting a proton onto some sort of base here, we would have this ionization constant. Again, we're going to omit the water. The ionization constant for some weak bases appear in Appendix I, but we're going to see in just a second that if you know the Ka value, you can actually figure out the Kb value for a lot of these bases. Here is the exact same thing. I can set up a relation of increasing strength, and I did that by going to the appendix and looking up those Kb values. Another value that can be useful for quantifying the strength of an acid is something called percent ionization. And basically it's going to be how much either hydronium or hydroxide ions are produced divided by the initial concentration of the acid or base. So this is the initial concentration, not the equilibrium concentration. Okay, so this is how much I added, and this is how much of it I had at equilibrium, which makes it a pretty easy value to measure because I can tell you how much I initially added, And then I could use something like a pH meter or something to figure out the hydronium ion concentration at equilibrium. We'll multiply that by 100%. But it is a little bit less useful than K and KB because the percent ionization of a weak acid or base varies with the initial concentration. All right, it's typically going to decrease as the concentration increases. This is a result of Le Chatelier's principle and the fact that we're dividing by the initial concentration and not the equilibrium concentration. For the conjugate acid-base pair HA and A minus, ionization equilibrium equations and ionization constant expressions are, so we have two models here. We're setting up a system where we have a model acid and then we're taking its conjugate base and then we're looking at the ionization that it has with water here. Okay, I can write the Ka here for this guy and I can write the Kb here for this guy. Now if I add these two equations together and then cancel the species on either side, our spectator ions here, I'm going to arrive at this equation here. And that is the equation for the autoionization of water. And as we've learned before, when we add equations, we're going to multiply their constants. And in fact, when I multiply those two constants together, I get this product, which is the Kw of water. What this means is that I can rearrange this and now have a means of converting between Ka and Kb. All right, so Ka of a system is going to be Kw divided by the Kb of its conjugate base, and the Kb of a system is going to be Kw divided by the Ka of its conjugate acid. Now, because Ka and Kb have this inverse relationship, that means that the stronger the acid or base, the weaker its conjugate partner is going to be. So here where we have a relatively strong acid, the hydronium ion, its conjugate base, water, is going to be a very weak base. Over here where I have a very weak acid, water, its conjugate base, the hydroxide ion, is going to be stronger. All right, and then we can see that hold true as we go along into the center here, right? Hydronium is not, or ammonium is not a very strong acid, but ammonia is a fairly strong base. Okay. Now there's this figure in the textbook, and this is going to be very helpful to you to answer some of the questions. Okay, you can directly look up in here the strength of various acids and bases. One thing I do want you to keep in mind, though, is that this is a little interesting because we have this hydronium ion here, and then we have all these acids that are stronger than that. All right. And that's actually a little weird, and it's a little weird because, as we know, these Ka's go to infinity, so how are we determining what the order is here if they're all just infinity? So the reason that things were a little odd before with the hydronium and how we get stronger ones is because there's this thing called the leveling effect. And basically what happens is once a acid is as strong or stronger than hydronium and you put it into water, it's all going to ionize completely and just produce hydronium ions. So there's no benefit to being any stronger. You're only ever going to be able to produce hydronium ions. You're just going to dissociate completely and have that Ka that's at infinity. All right. This is the so-called leveling effect, where at some critical point, acid strength just breaks down and all acids are just strong acids and ionize completely. How do we measure the relative strength of these really strong acids? Basically, what we do is we put them in a less basic solvent, usually something like ethanol or something like that. So what we want is something that's going to be less ready to accept that proton, okay? Because it's less willing than water to accept the proton, we're going to be able to see that some of those strong acids aren't going to dissociate completely, and then we can go about measuring their relative strength in that solvent and then extrapolate that out and imagine that that would also be true in water. We can apply the same logic to strong bases, where we just go and find a less acidic solvent that's be less willing to give up a proton to that base. This is an important conclusion that we're going to have for binary acids. A binary acid means that I have some sort of element bound to hydrogen, and that could be multiple hydrogens as well. And basically what's going to happen is it has the inverse relationship to electronegativity, okay? Because we want a weak bond between a atom and a hydrogen in order for the hydrogen to be given up. We want a less electronegative atom for it to be bound to. So HF, where fluorine is our most electronegative atom, is a fairly weak acid. It binds tightly to that hydrogen. As we go down the table and move towards the right, we get weaker and weaker bonds, and we see stronger and stronger acids. So let's talk a little bit about ternary acids and bases. Now, ternary acids and bases are a situation where we now don't have the atom bound directly to hydrogen, but instead we have a atom bound to oxygen and then hydrogen. This could play out one of two different ways, okay? This bond could be broken and it could release a hydroxide ion, or this bond could be broken and it would release a proton. If the central atom has low electronegativity, bond A is more readily broken than bond B, okay? Hence bond A here is ionic, and hydroxide ions are released to the solution. Okay, so this guy doesn't want to bond oxygen very tightly, so it is willing to break that oxygen atom bond there and produce a hydroxide. If atom E has relatively high electronegativity, bond A is strongly covalent. Okay, bond B is weakened because electrons are displaced towards E. And then bond B is polar and releases the hydrogen ions to the solution, and the compound behaves as an acid. So if E really wants to have electrons, it will draw electron density through this bond towards it. It will strengthen this bond between E and oxygen. That will draw electrons away from this bond here, weakening it, and then a hydrogen proton will be released. So let's talk a little bit about oxyacids. This is when we have high electronegativities characteristic of non-metallic elements. So we have a non-metal bound to oxygen here. We see that these have high electronegativity, so these are all going to be acids. All right. And these are what we call the oxyacids. Increasing the oxidation number of the central atom E also increases the acidity of an oxyacid. Okay, so you can make an argument based on oxidation number here, where we would have to go back and review oxidation number in the chapter about Lewis structures, and see that the acid strength is increasing there. I prefer not to have to do this. It is nice to know this to be a fact, but I do want to mention that you can also always just go look up the Ka values for a specific acid and just compare those. So we've seen what happens when you have a high electronegativity in the central atom and you have low electronegativity in the central atom. But there are a whole bunch of elements, especially those near that diagonal line where the metalloids are, that separate the metals and the nonmetals on the periodic table, that have intermediate electronegativity. And when this happens, these tend to be amphoteric. They can behave both as acids and bases. An example of that would be like this aluminum structure here, where it could accept a hydroxide when exposed to strong base and act like an acid, or the case where it could accept a proton and act like a base.